Okay, so after isothermal process, so let's proceed immediately with the next process, which is isentropic process. So I would like to introduce you to two basic diagrams or charts that you need to be familiarized when you are dealing with isentropic process. So take note of this one, the basic definition of isentropic process. So it is a reversible and an adiabatic process wherein no heat is being transferred in your system. Adiabatic. Okay? So as you can see in the graph, PV is equal to C, that is your isothermal. So basically, it differentiates the graph between the isothermal and the isentropic process. So isentropic process follows this relationship, that is PV raised to K is equal to C. Okay? And also, sulat muna natin, that is PV raised to K is equal to C. So it is represented by a straight vertical line in your TS diagram. Okay? Because as you can see here, your entropy is constant. Okay? So that's the first thing that you need to do when you are dealing with processes of ideal gas. And on your gas cycles as well. You need to be familiarized with this diagram. Take note that the area bounded by your TS diagram is your heat. Okay? But if we evaluated this one, it doesn't bound a certain area. So that's why heat is 0. Yung sinasabi natin dito, no heat is being transferred. Okay? Next. So, from this equation or from this relationship, when we are dealing with isentropic process, you should also be thinking of isentropic relations. Okay, so in thermodynamics, there are three basic isentropic relations that you need to be familiarized with. Okay, so number one, so from this equation first, okay, so let's derive something out of nothing. Okay, so if we expand this one, we will have P1 V1 raised to K is equal to P2 V2 raised to K. So by performing separation of variables, I can rewrite this one as P2 over P1 is equal to V1 raised to K over V2 raised to K. Okay? So here we can simplify this further. So if we review your laws of exponent, if I have two different variables raised to a same power or raised to a same exponent, I can simplify this one by writing it into a certain quantity. Okay, so that is quantity A over B raised to 2, or simply your exponent. So let's perform this here in this equation. So we will have P2 over P1 is equal to quantity V1 over V2 raised to K. So this is your first isentropic relation. Okay? Next. So from this equation, so if we review our combined gas law, that is P1 V1 over T1 is equal to P2 V2 over T2. So think of it as if there are no pressure that is given in the problem, only temperature and volume. So therefore, we need to solve P2 over P1 from your combined gas law. So how are we going to do that? So let's isolate P2 over P1. That will be P2 over P1 is equal to T sub 2 cross multiply. We will have T2 over T1 multiplied by V1 over V2. Si V2 cross multiply natin sa baba. Okay? So as you can see, the variables are already separated. Next. So now, we know P2 over P1 is equal to this one. So let's substitute the term P2 over P1 to this one. So we will have T2 over T1 times V1 over V2 is equal to V1 over V2 raised to K. Okay? So we need to isolate T sub 2, T2 over T1. So v1 over v2 here must be cross multiplied. So let's divide both sides by v1 over v2. Okay, so this one will cancel out. So leaving us with T2 over T1 is equal to quantity V1 over V2 K over V1 over V2. Okay, so as you can see here, if we review again your laws of exponent, so if I have x raised to the power of 5 divided by x to the power of 3 or x cubed. Okay, so as you can see, we have the same base. Our base here is x. So if you're going to evaluate this integral, so if you're going to evaluate this exponent, so you need to copy the base first, right? So you copy the base, and then since this is division, you need to subtract your exponent. Okay, so as you can see here, we can simplify this one as x raised to 2. Okay, we can do it here because this one has an invisible exponent of 1. So we will have t2 over t sub 1 is equal to, copy the base in this term, we have the base of v1 over v2 raised to, so the exponent, as we did here, they will be subtracted from each other. So that is k minus 1. So this is your second isentropic relation. Okay? So now, what if there are no volumes given? Because as you can see in the first two equations, they are dependent on volume. What if it's the given is pressure and temperature only? So from this equation, we need to solve for v1 over v2. How are we going to solve for v1 and v2? So we will use equation number 1. So p2 over p1 is equal to v1 over v2 raised to k. So if you're going to isolate this one, so we need to raise this by 1 over k, both sides. Okay, so 1 over k will cancel the exponent, leaving us with v1 over v2 is equal to quantity p2 over p1 raised to 1 over k. Okay, so now we have v1 over v2. We can plug it in our second equation. We will have t2 over t1 is equal to, so v1 over v2, we know that is p2 over p1 raised to 1 over k, quantity k minus 1. Okay, so now by laws of exponent again, if you have an exponent, raised to a certain exponent, let's say you have x squared cubed. So if you have exponent raised to an exponent, so you need to multiply this one, or simply that is x raised to 6. So you will have t2 over t1 is equal to p2 over p1 raised to k minus 1 over k. So this is your third isentropic relation. Okay? Next, so other parameters such as work, enthalpy, entropy. So entropy, we will discuss it later on once we solve the problem. So the next thing that we need to derive is work. Okay, so for work, we know that the non-flow work is equal to the integral of p dv from point 1 to point 2. And it says that it follows the relationship pv raised to k is equal to c. So therefore, p is equal to c over v raised to k. Okay? So if you substitute that, we will have integral of c over v raised to k dv. So let's remove c. We will have the non-flow work as c integral of dv raised to v divided by v raised to k. So if we perform integration, so v raised to k will be on the numerator. We will rewrite this one as c integral of v raised to negative k dv. So if you perform power rule here, that is, if I have u raised to n, so that will be u raised to n plus 1 over n plus 1. Okay? So now, I can have this one. So c integral of v raised to negative k plus 1. So let's remove already the integral. Okay? Over k plus 1, negative k plus 1 from point 1 to point 2. Okay? So we can distribute c. So if we simplify that, because we know c, so that is p1 pv raised to k equals c. Okay? So here, we can rewrite this one as, so p1 v1 raised to k so this one will be pv raised to negative k plus 1 times v, that is from here, that is v raised to k, so minus, so this is the upper limit minus the lower limit over, so this one, let's rewrite this one, 1 minus k. Okay, because math ethics, that positive will always come first. Okay, as you can see here, v2 is negative k plus 1, so we can dissect that. Okay, so how are we going to dissect that? So we know that if I have x squared times x cubed, so properties of exponent again, I will just add the exponent, copy the base, and then add the exponent, or simply this one is x raised to 5. So I can dissect this term. This will be p2 raised to v raised to negative k multiplied by v2 raised to 1 times v2 raised to k minus, same goes with this one, p1 times v1 raised to negative k times v1 so raised to 1 times v1 raised to k, so divided by 1 minus k. So as you can see, negative k plus k, that will be 0. So if I have x raised to 0, that identity will be equal to 1. So this 2 will cancel out, this 2 will cancel out. Okay, so leaving us with the non-flow work for an isentropic process, that is p2v2 minus p1v1 over 1 minus k. Okay, so these are the critical parameters that we need to identify. Okay, so in the next video, let's try to solve for problems related to isentropic processes by using isentropic relations and also the non-flow work. So I hope to see you on the next video.